you go down to the pad, please? So we're going to finish our discussion of Laplace transforms and various properties. Another property we'll look at is multiplication by t. So here, suppose you have a signal f, and we make a new signal, which is f, except you multiply by t. So that means, for example, if f looks like that, g looks like this. It's the same thing, only it's growing like that, growing linearly. So that's sort of the picture with f and g. Well, it turns out that the Laplace transform, when you multiply by t, time, the Laplace transform of g is very simple. It's minus the derivative. Now, what's sort of nice about this is there's an obvious parallel here, which you'll get more and more used to. But roughly speaking, this says that multiplication by the time domain variable, that's t, in the time domain, corresponds to differentiation in the frequency domain. So that's how people would explain this at a very high level. That's exactly the same as what we saw before, which was that differentiation in the time domain gets converted to multiplication by the frequency variable. Now, the details are different. For example, there's a minus sign here. Why is that? There's not that initial condition term. But at an abstract level, these are very, very similar things. That's the idea. Well, here it is. Here's the other way around. So here's an example, and this one's actually going to be important later this lecture. It's a Laplace transform of t e to the minus t. Well, we know the Laplace transform of e to the minus t. That's 1 over s plus 1. Okay? You multiply by t in front, and this is simply the derivative with respect to s. That's this. It's 1 over s plus 1 squared. Now, t e to the minus t, we're going to look at this later today, but it looks like this. For t small, it's 0. In fact, for t small, e to the minus t is about 1, and this thing looks like t. So it kind of goes up like this. What it does is it goes up, has a maximum, and then falls off. The maximum occurs at t equals 1, like that. Right, this is something you should probably know about. Now's not a bad time to mention it for the first time. This is a product of two things, one of which is getting bigger and bigger and bigger. That's t. The other of which is getting smaller and smaller as t gets bigger. That's e to the minus t. What you probably remember or won't be surprised to find out is that the linear growth of t is eventually completely swamped by the exponential decay of the e to the minus t term. And in fact, the transition occurs right at t equals 1. So for small t, this is growing. For large t, this is very, very small. That's the idea. Okay. Now, to prove this property is very, very simple. You take the defining function, the definition of the Laplace transform, and you differentiate both sides with respect to s, and you get something very simple. Over here, you get f prime of s. Here, I differentiate this with respect to s, and all that happens is a minus t comes down like that, and I'm done. And you can see this is minus the Laplace transform of t f of t, and we have everything. Okay. One other property is exponential scaling. Here what happens is, suppose you take a signal and you're going to multiply by an exponential like e to the at. Okay? Then it turns out that the Laplace transform simply shifts. That's all. So roughly speaking, exponential scaling in the time domain corresponds to a shift in the frequency domain. And this should at least look very similar to something else we saw, which was a shift in the time domain, which we call delay. That corresponded to exponential scaling in the frequency domain. In other words, it corresponded to a term of the form e to the minus st, where capital T is the delay. So something very fishy is going on here. These things are looking beautifully symmetric. Now the details are always different, but they're looking very similar. So as an example here, if you know the Laplace transform of cosine t, which we figured out is s over s squared plus 1, the Laplace transform e to the minus t cosine t, which is a damped cosine, you simply, all you do is you take, this is exponential scaling with a equals minus 1. I just plug in, instead of s everywhere, I plug in s minus a, which in this case is s plus 1, and I get this. So I get s plus 1 over s plus 1 squared plus 1. And you can check, of course, by just directly integrating this result. This is easy. There's a question?
Could you explain again why you refer to the Laplace transform as a frequency domain?
Why I'm referring to it as in the frequency domain?
Yeah, why does Laplace transform denote frequency?
Oh, why does it denote frequency? Actually, it's a bit vague. It's not as simple as like 101 where you look at a sinusoid and the frequency is simply, it's the number of radians of oscillation you get per second. No, here, the only justification I've given so far, I gave one based on units. I said that if you look at e to the minus st, st is unitless. T is time, s is frequency. The physical units of s are inverse seconds. That's frequency. Okay, so I actually haven't given any justification beyond that, right? So I'm just asking you to hold on. The connection to actual frequency, like the frequency of a periodic signal, that's going to come out later. But for now, let's call s the frequency variable only because its units are inverse seconds. Okay. Actually, later this lecture even, or on Wednesday, we'll see other reasons and other interpretations of how s is a frequency. It's going to turn out it's not exactly the same as saying it's the number of bumps per cycles per second. It's not going to be that. Actually, it's going to be very interesting. The real and the imaginary part are going to have different interpretations, and we'll get to all that. So it's a good question. I haven't answered it so far, but I will, I hope. Okay. And the last of this long list of properties is our dear friend convolution. And here, I don't want to get into it because we're not really talking about convolution yet, but you'll get a hint now as to why it's important. So the convolution of two signals is simply given by this integral, and we'll talk in much more detail later about what that means. Right? Shouldn't mean much to you now. It's just a formula for an integral. Well, it turns out that in terms of Laplace transforms, the convolution of two signals corresponds to the product of the Laplace transforms. Okay? So roughly speaking, frequency domain multiplication, in other words, when you multiply two things in the frequency domain, when you multiply two Laplace transforms, that is the same in the time domain as convolution. Okay? So that's the main part. So Laplace transform, roughly speaking, turns convolution into multiplication. And in fact, if someone said to you, quick, tell me why, in one sentence, why the Laplace transform is useful, you would say two things. You would say, the Laplace transform turns differentiation into multiplication by s. Therefore, it turns differential equations into algebraic equations. Secondly, it turns convolution into multiplication. And so it turns horrible convolution equations, which you'll soon know are all around you and describe all sorts of physical phenomena. It turns convolution into multiplication. And so it reduces also horrible convolution equations into algebraic equations. So this is the reason really why it's useful. Okay, let me just say a couple of things about how you would find the Laplace transform. Now, of course, you can always just go back to the definition. And in fact, in some cases, that's absolutely the right thing to do. You just go right back to the definition of Laplace. You go back to the integral. And in fact, if you do something that's excessively clever, that's really clever and really fast, it's actually a good idea to go back and check that integral, especially if there's maybe high stakes or something like that surrounding your getting it right. But generally, you will simply have to know the Laplace transform of a lot of things. This is going to happen whether you like it or not, so I'm just telling you right now. You're going to have to know things. So 1 over s, you should know instantly, without looking in a table, is simply the Laplace transform of 1. Okay? The Laplace transform of an impulse of a single delta function is 1. Okay? And vice versa. So someone should walk up to you and say, what's the inverse Laplace transform of 1 over s? You should just say instantly 1. What's the Laplace transform of minus 8 over s? The answer is minus 8. This kind of thing. Exponential. You should recognize exponentials. So if you have an exponential like e to the t, that's 1 over s minus 1. And you should just simply know that. Now, of course, these are very easy to verify, but you should recognize it. In fact, it's probably more important to be able to do the inverse so that when someone walks up to you and says, the Laplace transform is 1 over s plus 5, what is the inverse Laplace transform of that? No, somebody tell me. E to the minus 5t, exactly. And there just shouldn't be any hesitation there. Sinusoids. Sinusoids look like Laplace transform of cosine is s over s squared plus omega squared. Laplace of sine is omega over s squared plus omega squared. To be honest with you, if I haven't taught this class for a while, I don't remember the numerator. The denominator I remember, and you'll know why soon. Why you should remember the denominator. I guess you're actually taking the class, so you have to actually get this straight between s and omega. But after you take the class, you'll forget it. But then it's going to come up over and over and over again in every other class you take, and then it's fine. So, but these you should recognize. Now, these at a minimum. Now, these, if you combine this with a little table of Laplace transforms like we handed out to you, and these properties like linearity, scaling, and all these other properties I gave above, you'll get pretty far. You'll get pretty far. This is sort of a synthetic method. It's the toolbox method. You know a couple of these things, and then you know a couple of these things, and then you kind of know a whole bunch of little ways to combine them and stuff like that. It'll get you pretty far. And as I said before, if you do something excessively clever, right, you're very proud of yourself because you just expressed something as a triple convolution with something that was delayed and all that and all this, I'd go back to the formula just to check. That's what I would do. Okay, so, all right. We haven't actually done anything with Laplace transforms yet, so maybe the motivation isn't there. But hopefully we'll fix that. Okay, the other thing I want to make some, I'm allowed every day to be very vague and say stuff that's like useless and stuff. So this is probably my time. This is part of it. I'm going to use up some of it right now. So what I want to point out are some really pretty patterns that are emerging, that were emerging here. Okay, so basically, there's this beautiful symmetry between basically the time domain, like signals, and the frequency domain, which is to say they're Laplace transforms. Okay? And for example, if you differentiate in one domain, that corresponds to multiplication by the variable in the other. Now, the details are all completely different, and it's very important that you end up, that you remember the details. For example, the Laplace transform of f prime has a certain formula. It's not at all the same as the Laplace transform of tf of t. That has a different one. I mean, so it's just the flavor here, the spirit. Another is that multiplication by an exponential in one domain corresponds to a shift or delay in the other. Here's another one. If convolution in the time domain corresponds to multiplication in the frequency domain, then again, just based on aesthetic considerations alone, what do you imagine time domain multiplication of two signals? What do you think? We're going to even conjecture right now something. If I take the time domain multiplication of two signals, in other words, I have two signals and I form a new one, which is I just multiply them together. What do you imagine is the Laplace transform of H in terms of the Laplace transform of f and g? It's the convolution. It's exactly what it is. Okay? So there might be a minus sign or something like that thrown in there. I don't know. I mean, I could figure it out, but there might be a minus sign. But roughly speaking, there's going to be a convolution in there. And so that's exactly right. Even though we didn't give it here, this is sort of the idea. So it's actually important to have these patterns, these high-level well, I guess you need both, the real, the kind of the real skills, which is to say, to know that the inverse Laplace transform of 1 over s plus 5 is e to the minus 5t. But at the same time, you might want to think about these higher level things just to, that's to kind of guide you and stuff like that, put it all in perspective. Okay. Now, how this goes in the really big picture, the real big picture here is that after this course and a whole bunch of others, what will really happen is you'll end up, this is just simply a second language. That's what the frequency domain turns out to. It's just a second language. And in fact, like all second languages, it's not necessary. In other words, if people were smart enough to understand convolutions well, or differential, if human beings could look at a differential equation and go, oh yeah, sure, that's going to take at least 8 or 9 seconds before it settles out. That's not acceptable, right? Then we wouldn't need any of this. So this is just a language where humans get more picture, get a better idea or feel for some horrible convolution equation or something like that. Okay. Now what will happen is, like many languages, you will eventually, probably 2 courses from now, you will actually end up thinking in the frequency domain. And in fact, there's whole areas of engineering where, in fact, people not only, they just think in the frequency domain to the point where they even sort of, they're even a little bit fuzzy on what happens in the time domain. Specifications, commercial contracts, all sorts of things. All the specs are given in the frequency domain. So, I mean, I give you one example. If you have, for example, the dynamics of fighter aircraft and all aircraft dynamics, it's given in the frequency domain. That's what it's given in the frequency domain. So you talk about, well, what we're going to talk about in the next lecture. But this is how you actually talk about points in frequency points in the complex plane to describe the dynamics or how an aircraft feels, how it responds when you pull the stick or something like that. Okay, and the same is true of a lot of other things, like, for example, signal processing is generally done this way. So, okay, same with a lot of circuit design and all sorts of other stuff. Okay, so that finishes up our whirlwind overview of Laplace transform, and now finally we're actually going to do something with it. So, as I said last time, we don't get confused. This is all very nice and interesting, but we actually haven't done anything yet. Now we're going to do something. What we're going to do is we're going to solve differential equations. And we're going to start with some very simple ones, one of which you already know the solution of from 101, and another that you don't. Now, these are classical topics, so you'd find this in any text on, systems and signals or circuits or something like that. It's all there. And let me just say a few things before we start. There's a reason, there'd be no reason to do this if basically you had to first study first-order systems, then second, then third, then fourth, then fifth. It would be a very, very long, 102 would be very, very, very long. So let me explain something about why it's actually worth the time to look at first and second. What's going to emerge, maybe next week, is the following. Is that the analysis of a 117th order system. So this is a 117th order differential equation, or some horrible giant circuit with 117 capacitors and resistors. That circuit or that system is actually, it turns out, to understand what it does, all you need to understand is up to second order. So we're going to see that next. I'm telling you that now. We're not doing this just because this has been done for 50 years. This has been done but that's why. Okay. So we'll start by looking at first-order systems. This is kind of review. So a first-order system is a first-order differential equation. We won't even have an input. This just says that the derivative of a signal and the signal are related by a proportionality constant. Okay? This is called an autonomous system because there's no input to it. It's not being driven by anything. And the solution of this differential equation is called the natural or unforced response. And you can write it several ways. Here I have a coefficient both on A and B. And there's a couple of good ways to do it. One way is to write it as ty prime plus y equals 0, where t would be up here, A over B. Now t, I wrote it as capital T as a mnemonic. The units of that constant up there are seconds, because whatever y is, whatever physical units y has doesn't really matter. It could be microamps. Then y prime is microamps per second. And whatever this constant is in front, its units are seconds. Okay? Or you can write it this way, y prime plus ry. R is a rate. That's the point. R is a rate. That's why it's called R. R is a frequency, because a frequency is the same as a rate. So here, for example, if y has units of microseconds or microamps, then this is microamps per second. That's microamps. So R has a rate of inverse seconds, which is frequency. Okay? So that's how to write this. Let's solve this differential equation. They're the same thing because t is 1 over r. And we'll use our new technology here, Laplace transform. So we'll take the Laplace transform of this equation. Well, the derivative of y prime is sy of s minus y of 0 plus that. Sure enough, differential equation has been converted to an algebraic equation for the Laplace transform. We solve for the Laplace transform, and we get that it's y of 0 divided by s plus 1 over t. And therefore, taking the inverse Laplace transform, y of t is y of 0 times e to the minus t over capital T. Now, by the way, this is a case where, although I have given you, theoretically, a formula for the inverse Laplace transform, it happens to be a useless formula. So this is a case where you should recognize, you should have been able to look at this and say what the inverse Laplace transform of that is, right off the bat. It's this. Well, this makes perfect sense here. You've seen this from 101. This is RC and RL circuits. There's a characteristic time, that's t, which was RC or R over L over R, sorry. And that's it. Now, here, we never said that t was positive, so t negative is a possibility. But if t is positive, it says that the solution of that signal decays exponentially. And capital T, whose units are seconds, that's the time it takes for the signal to decay by a factor of 1 over e, which is about 37%. One of those, one of the 6 or 8 constants that everybody needs to know. Okay. Another one is people just say 0.7 t is the half-life, is another way to say it. So, in other words, in 0.7 t, so what I'm saying is e to the minus whatever it is, 0.7 is 1/2. So that's the half-life. And exponential decay, of course, is observed in just a vast array of fields. And every field has a different name, but actually after a while you start realizing that they're all the same. It's the doubling rate or the half rate, half-life, they call it sometimes, all sorts of things. Now 4.6 t, or if in casual conversation, 5 t, 5 time constants, that's the time it takes to decay to 1%. Okay? So the time it takes for an exponentially decaying signal to become sort of indiscernible to the eye on a graph, on a plot, is about 5 time constants, which you know from 101. Now, if t is negative, then this formula gives exponential growth. And then the absolute value of t gives you the time to grow by a factor of e. 0.693 t gives you the doubling time, is what people call it. So that would be the doubling time. And 4.6 t gives you the time to grow by 100. So for some reason, usually, this is what people, in fields where things grow exponentially, people refer to the doubling time. Okay, so that's usually what you look at. So this would be, for example, if you're going to do, well, we'll get to some of that. So let's look at some simple examples. It's from all over the place. Here's your friend, the RC circuit. And the differential equation is RC v prime plus v equals 0. So here you get what you had from, you knew this from 101. So there's your, so in other words, any initial voltage here will leak away through the resistor. So if there's a voltage here, current flows, but because current's flowing, that says that charge is coming off the capacitor, and so the voltage is reducing. As the voltage reduces, the current is proportional to the voltage. So the rate of decrease decreases. And so that's of course why you get exponential stuff. Okay, this you already know. Here's one, population dynamics. So let's let y of t be the population of some bacteria at time t. Now, y of t, I guess in fact, is an integer. Okay, since the integer at the end looks like 10 to the, has a very large exponent after it, and it's even just a little blob of bacteria, there's a whole lot of them, we'll ignore that fact. So that's fine. It's a perfectly good model. So the growth or decay of a population might be given this way, that this is ddt of the number of bacteria in a population. Well, a very simple model says that the number of bacteria created, I guess by cell division, is proportional to the number of bacteria there are, with the birth rate, with B being birth rate. Okay? Then it's also there's the death rate. So you subtract the death rate. So this is the idea. Okay, in this case, the solution is, of course, it's the initial population times e to the b minus d t, right, which is the birth minus death rate. If the birth exceeds the death rate, that's exponential growth. If the birth rate is less than decay rate, this is exponential decay. And then you could talk about things like, for example, what would be the time for the population to double, assuming b minus d is positive? What is it? Just about. What? 0.693 divided by b minus d. B minus d, those are rates, right? Because it's sort of births per second, deaths per second. They're rates, they're frequencies, right? And so when I ask you for the doubling time, that's the inverse of a frequency. So it's 0.693 or 0.7 divided by b minus d. So that's the idea. Here's another well, this is actually a very important thing. It's thermal systems, first order. It's a very, very simple model. It says that you have a body which has a temperature above the ambient temperature. Okay? So the ambient temperature might be just here, air. This might be, for example, a new high-end processor. Okay? And its temperature could be 10, 15 degrees centigrade above the ambient temperature. Okay? Well, it's got all these fins in it and stuff like that. It's been very carefully designed so that when its temperature goes up, it loses heat. That's a whole field. And depending on the situation, especially for stuff at room temperature, not a bad model often is that the heat loss is proportional to the temperature rise. In other words, the hotter something is above ambient temperature, the faster the heat loss is to the ambient system. And that's all, of course, in watts. And joules give you energy, and watts gives you... so, in fact, for a certain type of mounting system with a certain fan running, people will talk about the constant A. They'll talk about the constant. It'll be given in whatever watts per degree C. In fact, you even see, that's amazing about where we are. I guess even on 101, you'll actually see big billboards with specifications of A given right on the billboard. It'll say so many watts per degree C. Okay, so the heat in the body is CT, where C is the thermal capacity. And so the differential equation you get is CT prime equals minus AT. The solution is the initial temperature times e to the minus t C over A. That's, of course, always a decay. Well, it could be a temperature rise if you start with a cold body and put it into ambient, then the temperature goes up because heat is flowing into it. Okay, so just another example. This is one that's actually, though, quite important in a lot of electrical engineering and computer systems, is thermal stuff. Okay, so much for first order systems. Now let's look at second order. Now it's going to get interesting. So here you have a second order differential equation. You have basically this says that there's a linear relation between a signal, its first derivative, and its second derivative. And in fact, it's actually useful to get an intuitive picture of what this means. Y is the signal. Y prime is kind of the trend in the signal. It's what's the signal doing. Is it increasing? Is it decreasing, or what? Y double prime is like the trend of the trend, right? It's the curvature of the signal. It doesn't have anything to do with whether the signal is increasing or not. Or another way to say it is, this is the acceleration of the signal. That's what this is, right? So the units, if Y were unitless, are unitless, inverse seconds, and inverse seconds squared. That's an acceleration. Well, I suppose it would be an acceleration if Y were in meters or something like that. But it's like an acceleration. And so the units of A, B, and C are completely different. B is a frequency. A, this is very interesting, is inverse seconds squared. It's a frequency squared. That's what A is. Okay, so these are very different constants. Or the physical units of A, B, and C are very different. The reason it's useful to keep this in mind is later when we write down formulas, it's actually you can actually get really far just by dimensional analysis. In other words, when you look at a formula, you just scan it to make sure that the units are right, and if you've got it wrong, 9 times out of 10, you will detect it right away because you're going to find out that it's not consistent units. Okay. Now, we're going to assume throughout that this constant A is positive. If this were negative, I could just multiply this whole differential equation by -1 anyway. And I get a new differential equation describing the exact same system. And now A would be positive. Okay, let's take the Laplace transform. That's what we know how to do. And here, I take the Laplace transform of the derivative. That's easy. The second derivative, I look back, 10 pages in the notes, and I get s squared, right? Which makes perfect sense after all. Double derivative corresponds to twice multiplication by the frequency variable. And then you get these two guys, which are related to the initial condition, and that. And then this is just an algebraic equation. After a bunch of algebra, you get an expression that looks like this. It says y of s is the Laplace transform is very, very interesting. In the denominator, it's a quadratic. In fact, the quadratic is precisely the quadratic with a, b, and c as the coefficients. Again, notice that the units are right here, right? Everything makes sense here. Hey, you know what? I was wrong. And you didn't actually stop me. I sound too convincing. Look, y prime is a rate. The units of b is seconds, and unit of a is seconds squared. You didn't stop me. Oh well, that's a warning. I sound good, but sometimes I can be totally wrong. But it sounds good. Okay, so back down here. Here's how I caught it. Look, s is a frequency, so as squared, we're in some deep, deep trouble if a is a frequency. A is not. A is in seconds squared. B is in seconds, and c is unitless. And now we're okay again. So sorry about that. But how come you didn't stop me? Oh well. All right. So we end up, the Laplace transform looks like alpha s plus beta over alpha s, as squared plus bs plus c. Okay. Well, in a sense, we're done. I mean, since we have this formula for the inverse Laplace transform, we've just solved every second-order differential equation. Well, as usual with all this, solving it is not the point. The point is actually solving it is part of the point. If you actually need an answer for something, you're going to need to solve it. But in fact, the really important part is to understand it. So that's actually what we're going to do now. But at least, you know, there's a solution right there. That's the solution of a arbitrary second-order differential equation. Well, comes up a lot. This denominator here, which is a quadratic, it's a polynomial. It's called the characteristic polynomial of the system. And we'll see it's actually going to play a big role in what y looks like. Okay? And it's going to turn out that the form of the inverse Laplace transform and its qualitative properties, like is it oscillating or growing or shrinking, is going to depend on this polynomial in a great way. Alpha and beta are two constants that depend on the initial conditions. So that's the idea. Now again, if people were smart enough, there would be nothing more to do, and we could just look at this, and I could tell you, I could look at you and say, so I don't know, what do you think if A is 1, B is 2, and C is 1? And you'd all look at it for a while, and you'd go, oh, yeah, I see what's going to happen. Or if I said to you, well, I don't know, what if A is 1, B is 0, and C is minus 2? And then you'd all think for a minute, and you'd go, oh yeah, that's interesting, that's nice. So the point is, that's why we, well, anyway, I'm making the point. This is why we have Laplace transform. I don't know, maybe in a few years of, I don't know, a couple of generations of genetic engineering, and we won't need this anymore, because we could just have a conversation. Actually, the funny part is, guess what? Is actually, after this lecture, then we'll be able to have this conversation. And I'll say, what would happen if this is 1, 2, and 1, and you'll actually know. But then you can amaze your roommates or anybody who knows about differential equations by two of you could actually have a conversation about some differential equations and deny that you know anything about Laplace transforms. And just say, no, it's obvious if you make B a little larger that this thing will grow more rapidly. That's clear. And then, anyway, so, all right. So it's going to turn out that it's the roots of this characteristic polynomial that are going to determine everything. And the roots are, of course, this is, you know, the quadratic equation from high school. You know, it's minus b plus or minus squared, b squared minus 4ac over 2a. And we could check the units, and now that I've actually corrected myself, the units better work out right. I think they do. Okay. So these are the roots, and you can write it this way. In other words, so you can multiply this out, and this would give you a relation between, say, another relation. This gives you the lambdas in terms of the ABC. We could also, of course, get the ABCs from the lambdas. Now, as you learned, I guess, in high school or whenever it is, everything here depends on whether b squared minus 4ac, which is sometimes called the discriminant, is positive, negative, or 0. That's everything depends on that, obviously, because you're taking square root. Okay. So the simplest case is when b squared minus 4ac is positive. That's the simplest case. In that case, the two roots are real and they're distinct. They are specifically this one and this one. What's the average of the two roots, by the way? What's the average value of the two roots? They're both real. What's the average? What's the average of these two numbers? It's minus b over 2a. Okay, so that'll come up. Option 2 is they're real and equal. B squared is 4ac, and then the two roots are both minus b over 2a. And finally, option 3, the roots are complex. That's b squared less than 4ac, and this means lambda 1 is sigma plus j omega, lambda 2 is sigma minus j omega, and these are the traditional terms. So the sigma and omega are the real and imaginary parts of the roots of this characteristic polynomial, and there's many formulas, right? So for example, sigma is minus b over 2a, and omega could be expressed as square root 4ac minus b squared over 2a, or square root c over a minus b over 2a squared, and all that. So there's lots and lots of ways to express these things. So that's it. So these are the three cases. Now, I suppose, I guess actually I can't remember why on earth. I don't know, in fact, why would normal people want to solve quadratics, actually? I can't think of any reason. Can you think of any reason why normal people? Huh?
Projectile motion.
Oh, projectile motion. Okay, so projectile motion. Okay. So they're usually fine. So yeah, you can, if you're on the moon, you could find out how to aim a cannon or something like that. That's really useful. It's, that's why we've taught. No, it's a very important practical skill. It's why that's why we've taught, quadratic equations to children for the last 500 years. Yeah, it's very useful. Okay. All right. So I mean, the real joke is that actually for us it's actually useful, but I can't imagine why this would be useful to a normal person. But anyway, in that normal context of quadratic equation, if it tells you how to aim a cannon on the moon, great, that's fine. But they're usually, when b squared is less than 4ac, what that really tells you is, the meaning is really something like the problem is ill-posed. It really means there's something wrong. In other words, you should proceed along with this square root, and when you take the square root of a negative number, you should exit with some awful exit code, like you fed in nonsense parameters, like a negative mass for your projectile, or something like that, right? That's what it means. Actually, for us, it turns out that the situation of complex roots is, number 1, more common than real, and number 2, more useful. Very interesting. So that's the idea. We'll see that. Okay. So we're going to look at these three cases separately. Let's look at them separately. So the first is real distinct roots. There's lambda 1 and lambda 2, and we can express the Laplace transform, which is this. Now, we have not seen what the inverse Laplace transform of that is. You could look it up in a book. But I'll show you a trick that you will actually learn, I guess, at the end of this week, which is this. I'm going to write this as this sum. And if you work out the details here, like, for example, if you just put these two terms on a common denominator, you'll get something where in the numerator you get r1s minus r1 lambda 2 plus r2s minus r2 lambda 1. And then that's got to equal that. And so these are these two equations here. And in fact, you just get these formulas here. Again, the formulas, I don't know. First of all, it would be unwise to trust my formulas. Although I would say the probability that they're correct is now probably about 95%. I don't know these formulas. I figure it out sort of from scratch every time you have to do this. That's probably the safest method. So if I write the Laplace transform, which is this special form, which is has a quadratic in the denominator, and it has a linear term or an affine term a degree 1 term in the numerator, you write it this way. Why do we do that? We do that because I know the inverse Laplace transform of this, and so do you. That's r1 e to the lambda 1t plus r2 e to the lambda 2t. And that's it. That's the solution. So this is very interesting. It basically says that we know the solution of that second order differential equation. First of all, the solution is a sum of two exponentials. That's kind of neat because the solution of a first order differential equation is a single exponential. Okay? The solution of a second order differential equation now is a sum of two exponentials. It's very pretty. It's very beautiful. Well, this only happens if there's some relation between the coefficients, right? That b squared minus 4ac is positive. This is what happens. So this fits sort of, this makes perfect sense. Now these lambda 1 and lambda 2, those are rates, just like in a first order system. And they are associated with time constants, which is 1 over those rates. Okay? Oh, the other interesting thing to point out here is, well, all sorts of interesting things. For example, the qualitative behavior of y now depends on the signs, for example, and magnitudes of lambda 1 and lambda 2. So if lambda 1 and lambda 2 are both negative, what happens to y as t gets big? What happens? It decays, yeah. And what if one of the lambdas is negative and one is positive? What would that mean about y? What happens then? It's not going to oscillate, right? Because what will happen is as t gets bigger, let's suppose lambda 1 is negative. This term, if lambda 1 is negative, this term gets smaller and smaller, right? Whereas this term is getting bigger and bigger, right? So you get something where sort of one term decays away and another one grows in importance, right? So that's kind of the idea. And if they're both positive, then the thing is pretty unambiguous. The thing grows with time. Although, you can have some weird things, like, for example, R1 could be negative and R2 positive. And then, as these two things growing, they could actually cancel at some point. Could they, so in fact, that the sum could actually go to 0 and then keep growing. Do you think it could go to 0 twice, by the way? Because what's your intuition? Couldn't, right? The exercise you should be doing now is you should be visualizing two exponentials, right? An exponential looks like this, and there's an exponential right here. Here's a decaying exponential. It could look like that. You could just draw a couple of exponentials. There's one like that. Here's one that decays very rapidly. Here's one that grows very rapidly. And so you can multiply these by various numbers, and you just add 2 and see the types of things you get. It gives you the qualitative feel for what's going to happen. Okay, so let's look at an example. So here's something that is not from 101. It's a second order RC circuit. So here it is. Resistor feeds a capacitor. Another resistor feeds another capacitor. And first, let's get the intuition about what happens here. Oh, our voltage source here is going to switch from 0 to 1 volt at t equals 0. Circuit was in static condition, meaning this voltage and this voltage were 0 beforehand. And intuitively, what's going to happen? Let's do that first before we write any equations. It's always the right thing to do. When this voltage pops up to 1 volt, that voltage there is 0 volts. You get 1 volt across that resistor. What current do you get flowing in it? What do you get? You get an amp flowing that way, right? Well, where does that current go? Some goes that way, some goes that way. But the voltage here is 0 volts, and the voltage here is 0 volts. So the current flowing through this resistor is what? 0. So 1 amp flows into that capacitor. And what is the rate of change of the voltage there if you have a 1 farad capacitor with an amp flowing into it? It's a volt per second, C dV dt equals I. 1 volt per second. So the voltage here, which is 0, initially starts climbing at a volt per second. Now the minute this thing gets above 0, current starts trickling off here, which causes the voltage here to rise, and so on. So what happens now is it's kind of like various buckets of water and so on and so forth. This thing goes up, a bunch of water pours into this one, and as the water level here rises, the leak to the second bucket kicks in. And so here's what we expect to happen. Both of these voltages kind of smoothly go up to 1 volt eventually. Okay? This one a bit slower than that one. Okay, so that's the intuitive analysis without any differential equations. Okay, now let's do the differential equations. Here's when you work out what the dynamics is. It's y double prime plus 3y prime plus y equals u. And from the initial So if you work out what happens here, the initial capacitor voltages are 1 volt. Oh, it switches from 1 volt to 0 volts. I'm sorry. So I gave you the description for this thing switching from 0 to 1. I meant it switches from 1 to 0. Okay. So you go through the various things here. Everything depends on the characteristic polynomial, which is s squared plus 3s plus 1. You plug in, you find out the roots of this are the following numbers: minus 2.62, minus 0.38. Now, before we even move on, it says the solution has this form. Okay? That's actually very interesting, right? First of all, it tells you, for example, for large time, what's going to determine the voltage drop for large time. Is this term bigger or smaller than that for t large? Yeah, much smaller, right? I mean, if t is 1 or 2, right, this thing is much, much smaller than that. So what happens is this term really plays a role only for a little bit of time at the beginning. Very soon, it's just this term. Well, that's kind of neat. It basically says that this second-order circuit with 2 capacitors, something happens at the beginning, but then after that, the thing kind of looks like just an RC circuit. But at the beginning, something fishy, something other happens. But why wouldn't you expect that? It's 2 C's and 2 R's. It's more complicated. You'd be shocked if the dynamics of this circuit was simply that given by an e to the minus t over RC. It's not. But this says, actually, after a little bit of time, it is. It's pretty close. So when you actually solve the solution, you get this. Now, of course, when you finish solving a differential equation, it's very good to go back, plug it in, and make sure it really does solve the differential equation. In other words, differentiate this twice and once. Add up the double derivative plus 3 times the derivative plus this, and you better get 0. If you don't, then it means you made a mistake somewhere. So that's the idea. So this first exponential here, that decays fast, basically within 2 seconds. The second decays much slower. The time constant associated with it is 2.62 seconds. And so that sort of makes sense. Now, we can also figure out a little bit about that from here, because you could come along and do something real sloppy here, right? You could do something like this. You could just say, well, all right, let me just move this capacitor over to here. If I do that, then we're back in 101 land. If we're back in 101 land, by the way, what happens then? If that's a 2 farad capacitor, 2 ohm resistor. What's the time constant? 4 seconds, right? Now the only minor problem with moving that capacitor there is it completely changes the circuit. But then you think, okay, well, moving that capacitor over for the convenience of being able to solve the circuit, what did it do? Did it make the circuit like slower or faster? And you think carefully about it, and you realize, oh, that made it slower, right? Because here, this capacitor is only it only has to charge through an ohm of resistance. I move it over here, and I have to charge through 2. So by moving the capacitor over here, I made it slower. That resulted in a time constant of 4 seconds. So again, this is total, it's important to understand what I'm saying. This is complete hand waving. This is not you should never do this like in public or something like that, or with lawyers around or something like that. This is just getting a feeling for what ought to happen here. This thing ought to have a time constant that is less than 4. Well, guess what? That's right, it does. It's about 2. It's 2.62 is about the time constant of this thing. On the other hand, you could do some other cheap stuff. Take this capacitor and move it over here. What's the time constant now? What is it now? It's 2. All right? Now, when you move this capacitor over here, is this circuit like faster or slower? It's faster, right? Because now the second capacitor has the benefit of not charging through this resistor. In fact, this resistor is gone. Okay. Now just by complete, total nonsense hand-waving calculations here, I guess this is what people used to call back of the envelope, whatever happens here, the voltage here rises, and it's got a time constant, or it falls. It's got a time constant that's faster than 2, but slower than 4. Okay. I'm just showing you this just because it's very important to not get too mechanistic about this. Okay. But the solution is completely consistent with that. The exact answer is the time constant is 2.62 seconds. Okay. Our hand-waving said it was between 2 and 4. Okay, so here is here's a picture of it. Here's a plot of it. And here, if you just looked at that, you'd say that's an exponential. Except if your eye zoomed in right around there at the front. That looks like an exponential. Sure enough, the time constants are widely enough separated that one decays rapidly and the other is slower. This looks like if I were to draw a line like right here, this thing here is, for all practical purposes, it's an exponential, a single exponential with a time constant of 2.62 seconds. That's what it is. You're only aware of the fact that this is a second-order system for small times. And here's a plot showing on small time what it looks like. And in fact, the fact that this is flat makes perfect sense. What that says is that voltage on the second capacitor can't do anything until the first capacitor charges up, because it gets charged off the first one. Everybody understand that? In other words, this capacitor it gets charged by the voltage here. It has to wait until you build up some voltage here before you can get some serious charging action over here. What that means is that for small times, the voltage stays 1 for a while. I guess discharge is the right way to say it. But okay, so that's an example. Okay, let's do the real and equal root case and see what happens. Actually, we're sort of right at our boundary of time, but it's easy enough to work out. We'll see how it works. Here, to say that the roots are real and equal, says that b squared is equal to 4ac. And you express y as this expression, which you then write out this way with these coefficients. Now you take inverse Laplace transform, and you get yet another formula. You get something which is a linear combination of an exponential. That's hardly any surprise to us. That's everything we've seen. But now we see something new for the first time. We see a t e to the lambda t term. If lambda is negative, that's a term that looks like this. That's this kind of thing. Okay? If lambda is positive, it's something that looks like this. It gets big, big, like that. Okay? So what's happened now is we're actually seeing something we have not seen before, which is a qualitatively new type of behavior. It's a type of behavior where a signal can be, a system, something can be small, 0 in fact, rapidly grow, and then start shrinking. Okay? So you haven't seen this in first order circuits. Okay, so we'll continue this next time.